Hey guys, Ms. Gosling here. In this video, you are going to learn how to solve all of the practice problems for Unit 4. I'm going to go through all of them in one video, so this is going to be quite a long one. Feel free to skip around through this video as you are working through the different practices on your own. So with no further ado, let's go ahead and get started with the 4.2 practice. So with our easy problems, with our first problem, we're being asked to find the period of a pendulum of length 50 centimeters. So I know period is given by 2 pi times the square root of L over G for a pendulum. Thus, my period here is going to be equal to 2 pi times the square root of my length in meters, which is 0.50, divided by the gravitational acceleration, 9.8. So throwing that into my calculator, I get, let me go ahead and take a moment to throw that in. I get that my period is 1.4 seconds. Next, let's go ahead and find the period of a mass of 100 grams oscillating on a spring of constant 390 newtons per meter. So since this is a spring, my period is equal to 2 pi times the square root of my mass divided by my spring constant, or 2 pi times the square root of my mass in kilograms, so 0.1 kilograms, divided by my spring constant, 390. So again, that's 2 pi, sorry, I'm going to go ahead and add this in again, 2 pi times the square root of 0.1 divided by 390. Putting that in my calculator, I get that my period is 0.10 seconds. Both these problems are pretty straightforward. We're plugging and chugging with numbers into an equation. We don't even have to do any algebra. The only thing that's important to know is that we want to make sure that all of our numbers are in our SI units. Moving on to 3 and 4. In problem 3, we have an object oscillating on a spring with a spring constant of 100 newtons per meter and a period of 0.5 seconds, and we want to find the mass of the object. So using our spring equation, T equals 2 pi times the square root of M over K, I can go ahead and I can isolate M. So I'm going to divide both sides by 2 pi, and that will be equal to the square root of mass divided by K. Then I'm going to square both sides and then multiply by K, giving me that my mass is equal to K times T over 2 pi, quantity squared. Thus, plugging my numbers in, I get that my mass is equal to 100 times 0.5 divided by 2 pi, quantity squared, giving me a mass of 0.63 kilograms. Finally, let's look at question 4. An object oscillates on a pendulum with a period of 0.5 seconds, and we want to find the length of the string. So since we know this is a pendulum, we're going to use our equation T equals 2 pi square root of L over G. And following the same algebraic steps we did for problem 3, we get that L is equal to little g times T over 2 pi quantity squared, or 9.8 times 0.5 over 2 pi quantity squared. This gives us a period of 0.062 seconds. And those are our easy problems. Now let's go ahead and move on to our medium problems. So in this picture, we have a mass that is being pulled around. It's pushed to point A, that is going to oscillate in simple harmonic motion between points A and C. So, we know that the block takes 40 seconds to make 20 oscillations, and we're first asked to find the period of oscillation. So we know that period is the amount of time that it takes for one full cycle. So in this case, it takes 40 seconds to do 20 oscillations. Thus, each separate oscillation takes 2 seconds to do. So our period is going to be 2 seconds. In part B, we're being asked to find the spring constant of the spring given the mass of the box. So we know that T is equal to 2 pi times the square root of M over K. Thus, T over 2 pi squared is equal to M over K. Therefore, K is equal to M times 2 pi over T quantity squared. And I do that by essentially cross-multiplying. So if I multiply k to both sides, and then I divide each side by t over 2 pi squared, that's how I get this equation. Plugging my numbers in, my mass is 0.15 kilograms times 2 pi divided by 2, since that's my period. If you're going to be fancy, you can also cancel those 2's out, and that gives us that our period is 0.15 pi squared. Or, a little more simply, 1.48 seconds. Finally, for part C, we want to figure out what length pendulum would result in the same period. So we know that t is equal to 2 pi times the square root of L over G for a pendulum, and we want our pendulum's period to be 2 seconds. So, solving for length, we get that length is equal to t over 2 pi quantity squared times little g. Thus, our length is equal to 2, since that is the period that we want our pendulum to have, divided by 2 pi, again quantity squared, times g. Thus, we would need to have a pendulum of length 0.99 meters, or 99 centimeters, to have the same period that this spring does. So now let's get into our IB problems. First, we want to describe the conditions required for an object to perform simple harmonic motion. And this one actually should be pretty easy. It's just writing from your notes. Remember, we said that there are 2 key conditions. First, there needs to be a restoring force. And really, we can I'm actually going to go ahead and combine our 2 conditions into one. The key is there must be a restoring force proportional to a body's displacement from its equilibrium position, or just displacement from equilibrium. And the object needs to have been displaced. Or maybe it must be released from a displaced position. So next, let's look at number 7. An object of mass m oscillates in simple harmonic motion on a pendulum of length L with period t. The length of the string doubles and the mass of the object halves. What will be the new period of the pendulum? So we know that t is equal to 2 pi times the square root of L over G for a pendulum. So that means that the mass of the object, all that information, is completely extraneous because it's not in our equation. So our t is given, again, by 2 pi squared of L over G, and then we double the length of the string, giving us a new period of 2 pi times the square root of 2L over G. This is the same thing as writing 2 pi times the square root of L over G times the square root of 2. So I can take that square root of 2 out of, and kind of put it under its own separate square root sign, which is helpful because this is equal to our original period. Thus our new period is equal to our old period times the square root of 2. Finally, we have an object of mass m oscillating in simple harmonic motion on a spring of constant k with period t. The spring constant doubles, and the mass is halved, so we have to find the new period of the pendulum. So for a pendulum, it's not a pendulum, it's a spring. That's a typo on my part. So we want to find the new period of the spring. For a spring, we know that t is equal to 2 pi times the square root of our mass divided by our spring constant. And that's going to be our period for our original spring, since that's the data we have for our original spring. Our new spring is going to have a new period equal to 2 pi times its mass, which is m over 2, divided by its spring constant, which is 2k. We can rewrite this as 2 pi times the square root of m over 4k, or 2 pi times the square root of m over k times the square root of 1 over 4, or noting that this is t, we can just call this t over 2, since the square root of 1/4 is just 1/2, right? Because the square root of 1 is 1, square root of 4 is 2. And so that is our answer for our last IB problem for ESO. Okay, so with the Agile extension, I'm going to go ahead and I'm going to start by just drawing a picture of what's happening. So here is our box. It's at an equilibrium here at point B. At point A, I'm going to draw points A, B, and C. At point A, our spring is really tightly bound. So we've got a nice tight coil, and we're at our maximum height. At point C, again, just drawing out A, B, and C, our spring is going to be a lot more extended, a lot looser, pulled out when the box is at point C. So we're at our equilibrium at B and at our maximum and minimum at points A and C. So given our position time graph, starting at point B, let's go ahead and draw our velocity time graph. So at point B, since we're in simple harmonic motion, we know we have to be going really quick, traveling the most quickly when we're at our maximum, when we're at equilibrium. And since we're going to the right in the positive direction, we must have a quick velocity in the positive direction. So we're going to be at a maximum for our velocity versus time graph there. Then at point C, which is where we're going to go next, we're going to stop so that we can, and so instead of continuing to move to the right, we're going to start to move to the left until we get to point B again. And again, at point B, we're going to be moving the fastest we move as we go in the negative direction now towards point A. Then we'll hit point A, stop and turn around, and have a velocity of 0, and so on and so forth. So I'm going to go ahead, I'll connect these dots, and then I'll continue drawing the rest of my graph. Again, continuously kind of seeing the same pattern as I go through, as I stop at point A, go back through point B, speed up as I go to point B, slow down as I go to point C, stop, speed up again through point B to point A, and so on and so forth. And you'll notice that my position versus time graph is a sine function, and my velocity versus time graph is a cosine function, which is exactly what we expect to see, since velocity is the first derivative of position, and cosine is the first derivative of sine. Next, let's look at our acceleration graph. So for our acceleration graph, we are going to start off with an acceleration of 0 as we're at our equilibrium point, and when we're at that point, there is no spring force acting on our object. As we move towards point C, our spring is going to lengthen to the right, so our force is going to increase to the left. Since our spring force, just a reminder, our spring force is equal to negative K times our change in length. So our spring force is going to increase in the negative direction. Then as we go back through B, as our spring's extension has decreased, we're going to go back to a force of 0. Then as our spring condenses, as it moves towards point A, our force is going to increase, and therefore our acceleration is going to increase in the positive direction. Then as that force pushes us back towards point B, once we get to point B, we'll be again having 0 forces acting on us and therefore no longer accelerating. As we move towards point C, our spring is going to lengthen in the x direction. Thus, our force will be towards the left, the negative direction, and so on and so forth. So let's go ahead and draw this graph, really taking my time to make sure it looks at least somewhat nice. Your graph should definitely be neater than mine is here, just because I'm rushing just a little bit. Looking at this function, we can see that this, just double checking my work, I can see this is a flip of my sine function, otherwise known as a negative sine function. And again, checking back, I know that acceleration, again for folks who have done calculus, acceleration is the first derivative of velocity, and the first derivative of a cosine function is a negative sine function. So this is, again, exactly what I would expect mathematically, and it also matches with what I'm seeing in my picture and with what I know about forces. Now let's go ahead and move on to our energies. And I'm going to do kinetic energy in a new color. We're going to look at that in blue. We know kinetic energy is at a maximum when my velocity is at a maximum. So that's at point B. So at every point B, we're going to move, every time we go there, we'll be moving quickly. And it doesn't matter what direction we're moving in, we have a lot of kinetic energy because we are fast. When we're at point A and point C, on the other hand, we're stopped. So our kinetic energy will be 0. And so our kinetic energy function is going to look a little bit like this. And again, this is kind of what we'd expect, right? To do our kinetic energy graphs, we keep any positive components of our velocity graph essentially the same. Obviously, the magnitude is going to increase in a way I can't really do here since it is proportional to velocity squared. But since our kinetic energy is proportional to velocity squared, all of our negatives are going to become positives. So we're flipping all these negative components of our velocity time graph over the x-axis, giving us exactly what we expect to see as our kinetic energy graph down here. Finally, we look at our elastic energy. And our elastic potential is going to be at a maximum at points C and A. As we are at our highest, or as we are at the place where our spring is stretched out the most. So let me go ahead, let's draw those maxima for our A and C positions. When we're at point B, on the other hand, our spring isn't at all condensed or at all expanded, so that means that our elastic potential energy is going to be 0. So here we have our elastic potential energy. And you can see this is, again, kind of mirroring my position graph, and all of my negative positions have been flipped over to the positive side. But what's really important is that we can see that our total energy is going to be constant this whole time, because when our kinetic energy is at a maximum, our potential energy is at a minimum, and the opposite is also true. When our potential energy is high, our kinetic energy will be 0. So pretend this is a straight line. It's not quite. Yours should be a straight line. This is all of the practice problems from 4.2 fully worked out. Please let me know if you have any questions. Hopefully this clarifies any issues you were having as you were solving this on your own.